So we're now starting chapter 10, which is the last chapter of Algebra 2. It is dealing with our discovery into what are called logarithmic functions, logarithmic equations. If you took a meta perspective, a step back from this class and looked at what we've done thus far, specifically the last 4-ish chapters, you'll notice there's a trend. 4 chapters ago, we were dealing with quadratics, roughly. After that, we dealt with square roots. Square roots are the inverse of quadratics. Then, 2 chapters ago, we officially talked about inverse functions. So that we could then, in the next chapter, talk about exponentials. The reason I did that is because what we're about to discover are the inverse of exponentials. So we started off with 2 topics that were inverses, but we knew both of them, quadratics and square roots, so that we could build into exponentials, and we're going to figure out in this lesson what the inverse of that is. Majority of the second semester of Algebra 2 is largely a discussion around the idea of inverse functions. So we're about to go into logarithmic equations. Before we do that, I want to preface this. For those of you wanting to go into higher levels of mathematics, logarithms are used all the dang time. This is the first time you're going to be seeing them, so you might be a little rusty, and that's okay. When you take this again in pre-calculus, they're going to expect you to start getting good at them. Once you get into the calculus level, they're going to expect you to know logarithms like you know addition, subtraction, multiplication, division, and squaring something. It is such a fundamental process within a mathematics that if you try and venture too far into mathematics without logarithms, you're going to approach problems you cannot solve. Logarithms, just like addition and subtraction and multiplication and division, is a tool. It's a tool designed to do a specific job. This lesson, 10.01 and 10.02, is designed to show you the tool and to show you how it works, where it works, but equally important, when you should not use it. Addition is a really useful mathematical tool. We aren't using addition in every single mathematical problem. It has a time, it has a place. This is where logarithms came from. If I have the exponential function, y equals 2 to the x, we've dealt with this before. We've graphed this, we've messed around with it. The last chapter was all about modeling continuous and discrete growth. But if I asked you to find the inverse of this function, you're going to hit a roadblock. To find the inverse of a function, you take the x and the y values, and you swap them. If I did that to the exponential function y equals 2 to the x, we would get x equals 2 to the power of y. My goal then would be to do some matho-magics and eventually turn this into an equation, y equals something. There's your issue. You don't know how to isolate the y. If the y is an exponent, you all do not have the tools to get it out of an exponent. That's what logarithms are designed to do. Logarithms are one of the last gaps in your mathematical operations that you're going to be filling in. So here's how we do logarithms. If you are given an exponential function of the form a to the power of b is equal to c, if you are given that exponential function, you can convert it into or convert it from a logarithm of the form log base a. Now before I write what base a looks like, I want to describe how to write it, because this is something a lot of students write incorrectly. If I have x to the second power, that 2 we write kind of small and above it. That's called a superscript. Super meaning above, kind of like how Superman flies in the air. What I'm about to write is called a subscript. Sub means below. Like sub-0 literally translates to below 0. So I'm about to write the subscript. It's small, like a square would be, like an exponent, but it's written below the number, not above it. So it's log base a of c is equal to b. these two statements, a to the b power equals c, and the statement log base a of c equals b, they are the same statement. They are exactly the same thing. They're just written in two different formats. The first one is written in exponential form. The second one is written in logarithmic form. They both mean the same thing. They're just different ways of describing the same thing. So let me give you some examples so that we can learn how to translate between the two, but also how to read them. So here's a first example. If I have 5 to the third power, we all know that that is equal to 5 times 5 times 5, which is 125. That is a true mathematical statement. I could rewrite that into a logarithm. I could rewrite that into the logarithm log base 5 of 125 is equal to 3. Additionally, if I had that logarithmic statement, I could also convert that back into the exponential. In the same instance where I say that 5 to the third power equals 125 is a true statement, so is this. But we're reading it differently. For the exponential, we say 5 times itself 3 times is equal to 125. The logarithmic statement is going to sound similar, but with a key difference. It is saying 5 needs to multiply by itself until you get 125. In order for that to happen, you need 3 of them multiplied together. So it's saying 5 to what power is 125? The answer is 3. It's the same thought, just a different way of describing it. So my next example, now I'm going to do the other way around. I'm going to start with a logarithmic statement, like log base 2 of 16. Now before I just give that answer away, I want you to think about it. This is stating 2 to what power is equal to 16? How many 2's do you need to multiply to themselves in order to turn it into a 16? The answer is 4. If I wanted to convert that into an exponential, that would just turn into 2 to the 4th power is equal to 16. And again, I could also convert it back into a logarithm if I so choose. In the first lesson, in 10.01, I'm only going to ask you to do one thing. I'm simply going to provide an exponential function and ask you to rewrite it as a logarithm. Or I'll give you a logarithm, and I just simply want you to rewrite it as an exponential. And before I do that, I want to stress how important this is. Just like how factoring is such a critical idea to all the math that we've been doing thus far, there are certain problems you can't even start if you don't know how to factor. When we're dealing with logarithms, if you do not know how to convert between the two, if you do not know how to read a logarithmic equation or an expression, you will not be able to do this chapter. This is all predicated on the idea of knowing when and how to convert between the two formats. Because exponential form is really useful in certain circumstances. But there are other circumstances where logarithmic form is so much more useful. We're not going to get into it yet, but just trust me, it's coming. So problem number 1, I have 2 to the 5th power equals 32. If I wanted to convert that into an equally true logarithmic statement, that would be log base 2 of 32 is equal to 5. Problem number 2, I have 6 to the 2nd power equals 36. As a logarithm, that would be log base 6 of 36 is equal to 2. Problem number 3, I have 7 cubed equals 343. If I want to write that as a logarithmic statement, that would be log base 7 of 343 equals 3. So that's how we convert from an exponential to a logarithm. The next three are how I convert from a logarithm to an exponential. So problem 4 says log base 9 of 81 equals 2, which is true because if you ask yourself, what power do you need to bring 9 to in order to turn into an 81? The answer would be 2. And that's what it is as an exponential. 9 to the second power equals 81. Problem 5, log base 4 of 64 is equal to 3, would turn into 4 to the third power is equal to 64. Now before I do problem number 6, there's a little twist to it. If you read it, I'm sure you'll catch it. I want to remind you there are certain things that mathematicians do that we do purely because we are lazy. For example, a cube root is a radical symbol with a little 3 as a superscript. A fourth root has a little 4 as a superscript. You ever notice how the second root doesn't have a superscript? The reason we do that as mathematicians is, be honest, we're lazy. We use square roots all the time. Eventually a mathematician's like, oh, do I have to write that 2 every single time? Can I just not put the 2 and we'll all agree that if you don't see a number there, there's a 2. Same instance, if you have x to the third power, right, x superscript of 3. X to the fifth power is x superscript of 5. But x to the first power, we don't write a 1. Because again, we deal with x to the first power so frequently, mathematicians just kind of agreed, like, can we just agree that x to the first power, we just don't write the 1, and we'll all be on the same page, and it means we have to do less writing? Or even if you have x by itself, there's an invisible 1 being multiplied in front of it. We all just agree that we just don't write the 1 to save us a little bit of time because we deal with x by itself all the time. Logarithms are the same. There's a specific logarithm we see all the time, and so we said, we all agreed as a math community, can we just not write the base, like problem number 6? There is no base written for that logarithm. Can we just not write the base? Because we use log bases of 10 all the time, can we just not write the base of 10? And that's what we do as a math community. If you do not see a base written for a logarithm, the base of the logarithm is 10. And then that written as an exponential will be 10 to the third power is equal to 1,000. I will also forewarn you, there is another logarithm that we also do not write a base for. We will go over that later. But if you review what we did in the last chapter, you might be able to figure it out. So this is what you're doing in 10.01. We're just translating between the two and simplifying. 10.02, we're going to start solving these things. So in the first lesson, just relied on your fact of knowing how to convert between the two. In the second lesson, now you need to know how to read them, because I'm not going to give you the answer. Problem 1, I have log base 2 of 16. The way I read that is I ask, 2 to what power is equal to 16? The answer is 2 to the fourth power. And if you didn't believe me, pretend it's equal to x. You could have rewritten this as 2 to the x power equals 16. And then that 16 could be rewritten as 2 to the fourth power. Well, if the bases are the same, then the exponents must also be the same, which is why the answer is 4. Problem number 2, log base 3 of 81. That's just asking 3 to what power is equal to 81. The answer is 3 to the fourth power. Problem number 3 is saying log base 5 of 1 over 25. So 5 to what power is 1 over 25? Well, I can turn a 5 into a 25 by squaring it. But if I want to turn it into a 1 over 25 using powers, I got to flip it. The way we flip values with exponents is we make the exponent negative. So that's going to be negative 2. Problem number 4, I have log base 0.25 of 64. I don't know about you, decimals scare me. I'm going to turn that into a fraction, because fractions are nice. 0.25 is 1/4. So this is saying 1/4 to what power is equal to 64? Well, first I got to flip the 1/4, so I know my answer is going to be negative. and I need to turn a 4 into a 64, I do that by cubing it. So the answer is negative 3. Because 1/4 to the negative third power were to turn into 4 to the third power, and 4 to the third power is 4 times 4 times 4, which is 64. These are the kinds of questions logarithms are much more keen on solving. Here's the critical piece of information I'm going to tell you right now that you all need to know for logarithms. Logarithms are like addition, subtraction, multiplication, division, squaring, square rooting. There's a time and a place that they are useful. There's a time and place logarithms are useful. Here's when logarithms are useful. If you are trying to solve for something that is an exponent. For example, problem number 1. I want to solve for y. Y is a power. This is what logarithms are designed for. If you are trying to solve for something that isn't an exponent, don't use logarithms, ever. They are not designed for that. So for problem number 1, because I want to solve for y, I want to isolate the y, I want to get that function. The only technique that even I have to solve this, with all my mathematical background and knowledge, the only way I can get that y out of the exponent is with a logarithm. I first have to convert this from an exponential to a logarithm. When you do that, you're going to find that this is a problem we can actually just do in one step. If I convert this from an exponential to a logarithm, this would turn into this would turn into log base 2 of x plus 1 is equal to y. I just did the conversion. And now I just need to isolate y. Y is already isolated. That's the answer. Problem number 2, same thing. I want to solve for y. Y is an exponent. Therefore, I have to convert it from exponential form to logarithmic form. So this is going to turn into log base 5 of x over 3 is equal to 2y. Y is not isolated. There's a 2 in front of it. So I'm going to have to divide both sides by 2. And even though it pains me to write this, log base 5 of x over 3, all divided by 2, which you will learn is simplifiable, you just don't know how to do it yet, is equal to y. That is my solution. Problem number 3, I have 9 to the power of 7y minus 3 equals 2x minus 1 divided by 5. First step I got to do, because the y I want to solve for is in an exponent's location, I got to convert this into log base 9 of 2x minus 1 all over 5 equals 7y minus 3. Now I got to get that y by itself. So I'm going to have to add the 3 to the other side. Here's another critical thing. That log base 9 of 2x minus 1 all over 5. Until you learn the properties, nothing can ever go into the parentheses. Nothing can ever be taken out of those parentheses. Those parentheses are an impenetrable force field. Nothing can get in, nothing can get out. So that plus 3 is not going to go inside of the parentheses. I'm going to write log base 9 of 2x minus 1 all over 5, close parentheses, plus 3. You could have also written 3 plus the logarithm, the same thing. Eventually, you'll learn how to start getting stuff in and out of a logarithm. We do not have that ability yet, so you can't do anything. I need a small smidgen and a little bit more space, because next I'm going to divide everything by 7, and I will get log base 9 of 2x minus 1 all over 5 plus 3 all over 7, which pains me to write because that is simplifiable using the 7 properties of logarithms. But for right now, we don't know them, so we'll leave it as is. And then problem 4 is the one that gives students the biggest headache, or at least me the biggest headache. Because at this stage, a lot of you will get really used to solving with logarithms. You'll get so into the zone about solving with logarithms. You'll love the fact that logarithms are super, super easy and straightforward once you get used to them, that eventually you stop thinking about the problem and you just start doing logarithms for the heck of it. Logarithms are a tool. They have a time, they have a place. They are used to solve when the variable is a power. Problem 4. The y value I'm trying to solve for is not an exponent. I am not going to use logarithms here. I just have to divide both sides by 2. That's the answer. 361 to the 5x plus 9 all over negative 3 power, all divided by 2, is equal to y. This was a one-step problem that never involved logarithms. You need to know when, you need to know where, you need to know why.